Hello. Namaste to one and all present here. Welcome to IIT Gandhinagar. Welcome to FSC TCS 2024. I hope you'll have a really lovely week ahead of you. Right now, I am going to pass on the mic to Professor Rajat Muna for the inaugural address. Thank you.
Good morning to all of you, all those who are attending FSC TCS. FSC TCS has been a very long standing conference. I myself have attended this when I was doing my own research. Well, at that time, it was not in this present form, but FST and TCS were two separate things. But then I did attend it. I don't remember which one, FST or TCS, but one of them I did attend. Anyway, let me first of all welcome everybody here. Over 2 days that we are going to be here, we are going to see a lot of very interesting things. And what I'm told by Neil Dhara is that your kids actually, even in order to find out what your schedule is, you have to solve a puzzle. So you have to sort some things to figure it out. And there are, at least 6 dimensions to sort it. 5 are the holes and 6th one is what you have to figure out. So once again, the time is very conducive here right now, and weather is perfect. Do feel the campus is one of the most beautiful campuses that you will find, and take around, your tour in the mornings. You are actually going to see a lot of very interesting things. Of course, whole day will be in the conference, but subsequent to that, I'm told by Neil Dhara that there are a lot of very interesting activities which are lined up. So without saying much more than this, I once again welcome everybody and wish you the very best of the time and of the interactions that you're going to have here. Thank you very much.
Thank you, Professor Rajat Muna. Now we'll have the first invited talk for this session. I invite Professor Madhu to give away the first invited talk. The session chair for this session would be Professor Nutan Limay. Thank you.
So sorry for a little bit of confusion, but we have a few announcements that Neil Dhara will make, and we would also, as organizers, like to make some opening remarks before Madhu's session starts. And Madhu's session was announced at 9 a.m. So there are people joining online and so on. So I think it's better if we start at 9 precisely. So, yeah.
Yes, indeed. This is probably the first time that we are early, I think, in my experience. So running a little ahead of schedule, I'm very pleased to say. But in any case, good morning, everyone. Welcome to the first pre-conference workshop. Delighted to have all of you here. And we've lined up a few things. So hopefully you're going to have a great program and a great after program. And with that, I'd like to invite the organizers to make their opening remarks before we invite the first session chair.
I think, so maybe Akshay, Prajakta, myself, we'll all together be, and Olaf. So I think Olaf is on his way. I think he's, yeah, this would be great. Yeah, so. So I think I have to fill in, so let's start with the song. Okay, so hello everyone. We're very happy to welcome you all for the workshop of FSGTCS. And serving the invitations and on the webpage. We hope to make this event useful to FST and ECS as the directors and earlier. So we have speakers taking on diverse topics and the interaction in the breaks. So I hope you all the workshop. There are 8 invited talks and 6 contributed talks. So, is there something else you want to say?
No, that's fine, but we have still 7 minutes left.
So maybe we finish your demonstration and want to give it a try. You could start a shop now. She can the session sharing for that session. Thank you.
All right. Hello and welcome to the first session. I guess some people are just streaming in, but let's get started. So yeah, it's my pleasure to introduce Madhu, who's the speaker in the first session. So many of us know Madhu already, but just for the sake of it, I thought I'd make a few introductory remarks. Madhu is currently a professor at Harvard. He did his undergrad at IIT Delhi and then did his PhD at Berkeley. And he's been at many different places since. So he spent some time at IBM, at Microsoft Research, MIT, and now he's at Berkeley. I'm sorry, at Harvard. And so Madhu, as many of us know, is an extremely accomplished theoretical computer scientist. His research in general revolves around the theme of noise and reliability in all sorts of computation. And this spans many aspects of theoretical computer science, including pseudo-randomness, probabilistically checkable proofs, coding theory. And in general, he takes a much more general view of it, as you can see from the title of this talk, and we hope to learn much more from him. So Madhu, yeah.
Thank you, Shrikant, and thanks to the organizers for putting this wonderful workshop together. I believe we are celebrating something, milestones and motives. So I'll try to do something which is maybe also celebratory in nature. This is really a celebration of our field from the times of its origins to today and all the remarkable achievements that we've had. This is not really meant to be a technical talk where you will learn something, some theorem or proof that's new. It's really meant to be a way that you should start thinking about our field and about how global its presence is. So let's hope, yeah, okay, so this works. And yeah, okay, I know how to advance. Is there any chance we can get rid of that? Okay. So in this talk, so proofs and computation. So I want to say what this talk is not about. So it's not about computer-assisted proofs. And almost every time that I talk to a lay audience, scientific audience, and I say, oh, proofs, computation, the immediate thing is, how can a computer help you find proofs? And this talk is not really about that. There are lots of very nice works, not what we are interested in. But I think of what we are trying to think about as something much, much more fundamental and foundational. There is this triumvirate that I want to talk about: mathematics as a field, as an enterprise, computing as a field, as an enterprise, and the link that they have through proofs. And it's a link that goes in multiple directions. In fact, the whole graph is strongly connected, as you can see. So outline, well, I mean, this is a historic talk, so we'll start with prehistory, which is anything before 1950s, ancient history, which is 1950s to 80s, and so on. Now, I should credit the idea for this slide to Mihalis Yannakakis, who once told me that, what is standard is what you learned in grad school. So for me, recent history, grad school is recent history. Everything else is just ancient stuff, and anything more recent is modern, okay? So we'll talk about modern things which are only as recent as 5 to 10 years old. All right, so prehistory. So what is a provable statement? So the attempt to sort of understand what the formal basis of logic is came up very differently in many different civilizations. One sort of a, ancient civilization which definitely explored this question quite explicitly was the Greek civilization. Aristotle in particular started the school of thought where they were trying to model the notion of axioms and derivations and proofs and so on. So this is how mathematics relates to proofs, to understand that all of what we are doing in mathematics is somehow something related to something that is provable. Now, what changed Boole, I think, I personally, credit this paper of this treatise of Boole as a very significant step over here. He took proofs and embedded it into mathematics. So you can talk about what is a proof in the language of mathematics itself. So in particular, you have to start talking about not real numbers and complex numbers and how to extend it to even larger and larger sets, but an algebra which is over a much, much tinier universe of two elements, 0 and 1. And operators or operations which combine these variables which take these values to through this strange logic. And there was a very interesting kind of this paper that was, I haven't, this is called Axioms of the Laws of Thought, or the Laws of Thought. So it's really like deep. It's not just we are trying to do mathematics and capture it, but all of thinking. And the title of the book, which is kind of longer in side text, includes things like logic and probability in the title. So it's really like a pretty far-reaching concept. There's a very interesting kind of mathematics that he's developing, and one of those things starts with this thing saying, oh, we can use our mathematics to derive implications. So for instance, we all know that repetition, I will just tell you the same fact twice, it shouldn't add to your body of knowledge. A consequence of this is the principle of contradiction, that at the same time some fact cannot be true and its negation cannot be true. So how does he derive it? Here's sort of the proof that you see in this paper written, more or less in the same form as it was in that paper. So, x squared equals x, that's saying repetition doesn't increase knowledge. Now you can do some calculus to say either x or 1 minus x should be 0. And that's saying, at least one of these facts cannot be true. So it's very interesting that when everybody else was trying to extend the scope of mathematics by looking at larger and larger and larger sets of objects, integers, rationals, reals, complexes, here Boole went down and thereby found the entire core of mathematics. Okay, so somehow this is all of what we are doing, but all of it fits in this language of zeros and ones. Okay, this is the page 34 of that book, apparently. So how well does this logic capture mathematics? This started to become a sort of a serious exercise over the 80s and over the 19th and 20th century. So Cantor, of course, sort of was the first to encounter this problem and pointed out that there's something sort of inherently contradictory about trying to reason about all of mathematics. Hilbert didn't really completely internalize this and sort of was really very strongly believer of the fact that logic should be able to capture everything that we can do. And then Gödel came along with his incompleteness theorems, and I'll credit this version of the statement and its understanding to Scott Aronson and his lecture notes on this. So the statement that Gödel used was not the statement is not true, but rather the statement is not provable. So now this is a statement which either is true or false, and no matter which, you should not be able to prove the statement, because if you can prove the statement, then you've just proved that its negation is true. And if you have not proved the statement, then it's true, but unfortunately you haven't found a proof. So this is the statement that sort of leads to the incompleteness of, essentially tells you that any system of logic should be either inconsistent or incomplete. And then Church and Turing came along and basically said, really like this is a kind of a incompleteness that holds for any effective reasoning procedure, anything that we can think about. So it really captures thought as we want to go back and think about. Turing's contributions to our field, of course, we don't need to mention too much. I mean, I think it was an amazing thing, this model of a computer which has this finite state control and then an infinite read-write tape. Just, very, very, very simple model that captures every device that we are currently working with. It's quite remarkable that it's so powerful. And of course, this other thing that, this one machine that exactly, that can capture, once you have the universal machine, you don't have to really design new Turing machines. From now on, you just reduce to doing programming. So it's quite a remarkable thing. It's the reason our field is so successful, is the reason computers are so prevalent, because we can design one of these, buy it, and then use it to do so many different things later. Von Neumann changed this model slightly and called it a CPU and a RAM, and otherwise it's really the same kind of a principle. And this is much, much, much closer to the model of the day today. So this is where the story has gone so far. So proofs, in some senses, was the motivation for the introduction of these machines. Why did Turing invent the Turing machine? He wanted to say, look, a proof has to be something that's mechanically verifiable, but we don't have a mathematical definition of what is mechanically verifiable. And having defined a Turing machine, you could now say, okay, if something is mechanically verifiable if it's verified by this Turing machine. And that gives you a formal definition. And now you get to work with everything else that we've been talking about in a more, in a consistent way, in a well-defined way. And incompleteness, of course, says that there exist statements that are consistent with a system of logic, but will not admit a proof. But what this theory did not explain to us, and this is why I call it sort of prehistoric material, is, what difference does having a proof make? I mean, as mathematicians, or at least half of every one of us is a mathematician, I mean, why do we seek proofs for objects? Why not just, the fact, so many physicists actually tell me, why are you seeking proofs of P versus NP? I mean, it's P not equal, right? So why don't you just work with that assumption? I mean, we do understand how to work with that assumption very well. It's still that, we seek proofs for things that we completely, totally believe also. Why do we seek these proofs? What difference does it make? And it's very there in the P versus NP statement itself. So here are two different proofs, one of which is in our system of logic and goes through the step-by-step derivation, the first sentence, the second sentence, the third sentence, the fourth sentence, and so on. Each sentence follows in some simple, well-defined, previously, completely articulated way from the previously defined sentences, making it mechanically verifiable. And then the final sentence says, okay, something is true. But look, here is a completely equivalent, mechanically verifiable proof, which is, this proof has L lines, okay? Once I've told you this, I'm past Gödel's incompleteness, I'm past Turing's undecidability. It's just a mere matter of exponential search. I have to search through exponential in L possibilities and I will find it. That's mechanically verifiable, right? But we don't believe that this is what we really mean in a sense by mechanically verifiable. And this is the reason why we had to invent concepts like polynomial time computability and non-deterministic polynomial time as classes. So both are mechanically verifiable, but they are not equivalent in our eyes, and they should not be equivalent in our eyes. So our mathematics has to advance to capture this aspect, okay? So this leads us to the ancient history, the stage 2 that I want to talk about, efficient verification. I mean, we are seeing, look, the definition of a computer started by saying what is a proof, okay? Now we will see the definition of complexity starts by saying why is the old definition of a proof not sufficient, we need a new one. And this starts with a letter from Godel to von Neumann where he says, amongst other things, he says, look, if I want to find a proof of length L, if one exists, like, is there a mechanical way to find it? Something that works in time L squared or L to the 7 plus, something, or is it like 2 to the L or 10 to the L? So this difference between polynomial time and exponential time was explicitly raised in the work of Gödel, but he still did not define a universal class of polynomial time computable functions. That happened later in works of Cobham, who has the most common image on the web, but unfortunately not uniquely defining him. And Edmonds is the one, by the way, there's this beautiful book by Schmoyes and Williamson where I think you find this very nice quote due to Edmonds about saying very precisely that, look, I believe Hamiltonian circuit problem cannot be solved in polynomial time, and my reasons are the same as there are for every other mathematical conjecture, which is that I tried working on it and I failed. And I think there is a sort of a way of formalizing this more precisely using notions like non-determinism and polynomial time. So you've completely nailed down the sort of parameters within which you're going to play the game, but then it took more work to get to that point. But in any case, Edmonds definitely defined polynomial time for us. Hartmanis and Stearns defined the richness of polynomial time. And this very intriguing, I mean, this is not, maybe Hartmanis and Stearns were not the first ones to point this out, but the thing that's pointed out in their work, which is that, time complexity is very weird. The time complexity of 5 times L squared is really the same as 10 times L squared. And you're trying to find a proof of length L, but L to the 2 is very different than L to the 1.9. So how can you have the equality there which doesn't sort of transcend to proving L to the 9 is not L squared? This, I mean, it's a matter of defining the equality carefully, and that's what we're doing. But these are certain equivalence classes that really have this very intriguing behavior. And more time gives us more resources. So it's really completely clear that polynomial time becomes a well-defined measure of complexity of class of problems at this stage, and this led to the definition of P, the complexity class. And Edmonds' conjecture was really traveling salesman problem is not solvable in P. It took a little bit more time for us to formalize this. And once again, I would like to highlight the work of Cook in particular, who was really interested in the complexity of theorem proving. I mean, that is the title of the paper. We are not interested in, solving important optimization problems, not today, but that will come later. Levin concurrently discovered very overlapping notions in this idea that in his paper, in his thesis of on universal search problems, and these are like, even though there's a gap of a few years, these are really recognized today as sort of independent concurrent works. These two works formalize for us Edmonds' conjecture. They tell us that NP is the class of problems which have efficiently verifiable solutions. The prime example for us today is that of saying, given a theorem, find me a proof. Given a theorem and a length L, this is the length of the proof that I want to find me the proof in time polynomial in L. That is the class of problems that is equivalent to NP-complete problems, any NP-complete problem. So theorem proving was shown to be NP-complete, in particular by Cook, and its NP-complete problems are the hardest problems in NP. So definitely not something that I need to stress to this audience. So it's still very interesting to me that, so SAT is, sort of an NP-complete problem. It's one of the simplest formats for going to proofs. So if I want to state a theorem as a SAT theorem and getting a proof in the SAT form, it makes things much, much, much nicer. Domino tiling was shown to be NP-complete by Levin, and Gödel's question was really asking, is NP equal to NP? But now we have a formal definition. So this was, by the time we're looking at this, we're looking at 70s. And the theory might have been relegated to some corner of the universe if it hadn't been for the work of Karp, which was, I think, profoundly important. There is some 19 problems that he showed to be NP-complete. Many of these problems that look completely unlike any of the other problems in the same class. So suggesting that this is not just a phenomenon relegated to one tiny corner of the universe. I mean, we had Turing, we had undecidability, and undecidability took on many different shapes. And even then, we did not recognize the richness of the concept of universality as in Karp's work, where I think we completely said every aspect of what we want to deal with is going to be dealt with by computing, the theory of computing, and perhaps this notion of polynomial versus brute force search. So Karp's problems are really, really interesting and important to us. So some example problems: map coloring. Can you color this map with 3 colors or not? Is that, I mean, you shouldn't allow, okay, you shouldn't allow things like that, which happens only in very strange places of the world, but you should not have 4 adjacent, 4 clique in this graph, which should not be allowed for this question to be considered, but nevertheless. Traveling salesman problem. This is apparently a TSP tour visiting all cities of a certain population, 13,000 most populated cities in the US. And this is the optimal solution from some people who've actually managed to do this brute force search problem in feasible time. So these are kinds of examples of NP-complete problems. So the scope of the field is definitely pervasive. But what's probably more interesting is that really, it gives us a new format for stating proofs. So every NP-complete problem is a format for stating proofs. What do I mean by that? Suppose I use the fact that 3 coloring is NP-complete. What that implies for us is if somebody gives us a theorem statement written in some system of logic, some formal system of logic, along with a length L, saying this is the length of the proof that I expect, I can apply this function, mechanically computable polynomial time function, computable function f, and it'll produce a map with some polynomial in L regions. And if this theorem has a proof of length L, this map will be 3-colorable. If this theorem does not have any proof of length L, this map will not be 3-colorable. So everything about this system of logic, how new derivations can happen, etc., all has been wrapped into this function f, and we don't have to worry about it anymore. You look at a proof, you don't even need to know what the origins of this question are and why we are interested. We can mechanically go around verifying it. What does a proof look like? Well, a proof looks like an assignment of 3 colors to this map. So for each region, you say, what is the color? Is it red, blue, or green? And sorry, Srikanth was colorblind. So this is red, blue, and green. And if I actually look at those 2 pointed nodes, are they the same color or not? If they were an edge, okay, so proving that Srikanth is colorblind, they actually happen to have the same color. So this would be an illegally colored map, illegal coloring of the map if there was an edge between the 3rd vertex and the 9th vertex, okay? All right. So what's the advantage, by the way? Why are we looking for different formats for proofs? We know one way of writing proofs. What's the difference? Here is a proof where it's very easy to point to you that your proof is wrong. Okay, so if you give me a proof of a map and you say this is 3-colorable, I can just point to those 2 places, say, look at these 2 places. The coloring is supposed to assign distinct colors and you have the same colors. It's completely local to point out an error in the proof to you. Not every format for writing proofs has the same feature. This one does. So this is an advantage, and indeed different formats for proofs have different advantages, and this is something that we will explore in some of the upcoming moments. So digression, some of you have probably seen these kinds of slides before. Is P equal to NP? Of course, we don't know. If P equals to NP, we are in very interesting times. The cryptography that we have set up, the foundations for it as we have set up, rely on P being different from NP. If P equals NP, that's definitely dead. P not equal to NP does not mean cryptography is alive and can work, but if P equals NP, it's definitely dead, okay? But on the other hand, all optimization problems become easy, and so maybe we will live in the current world that we think we are living in, the world of machine learning, which is everything you want to, infer, you're able to infer. That's the kind of a situation which would be, but in a much more rigorous worst case sense. You get whatever you wish, if you can verify, if you can verify satisfaction. So you can replace mathematicians with computers in this universe. If P is different from NP, well, this is consistent with current thinking, so it's not going to change how the landscape of our field looks like. But on the other hand, the proofs will be very educational, and this may lead us to a more systematic way of building crypto systems where we are able to prove the soundness of every crypto system that we work with. Almost every crypto system that we work with, not almost every one, there is foundational works that we are doing which try to minimize the number of axioms, but a large number of crypto systems in practice just tend to work on their own assumption. So that's really not great for the field, and it would really be nice to unify the field a lot more, bring it closer to where the foundations of cryptography are taking us. Could also be independent of Peano's axioms, and there have been some works that have been trying to explore this. I won't comment too much about those. So what's the popular view on this thing? So there's an author, Keith Devlin, who wrote this book around the year 2000, a few years afterwards. There was the Clay Math Institute introduced these Millennium Prizes, and they had, I believe, 7 open problems at the time. And each one, the resolution of each one would lead to a prize of $1 million, okay? And in celebration of these Millennium problems, Devlin wrote this book and about each one of the problems, and then in the summary he says, look, of all the Clay problems, the P versus NP problem might be the easiest to solve by an amateur mathematician. So he probably thinks P is equal to NP because if, just to prove that a quintic does not have a solution in the method of radicals, Galois had to invent Galois theory. We don't think you're going to prove P is different than NP by some techniques which are elementary. No, I mean, it's going to be much, much more richer. But if you want to prove P equal to NP, yeah, it's completely possible. We get papers along those lines every day at every one of our top journals. So Devlin is probably thinking P is equal to NP, but Fortnau has a sort of response to this. If somebody shows P equal to NP, then he says, you should walk away with $6 million and not just $1 million. I think one of the Millennium Prizes was the Poincaré conjecture, and hence out of this picture, but the remaining 6 millions are still sitting there. And we can take all of them home because you can prove every theorem that you want. So that should be a reason to think maybe this will be the last question to be resolved on this list, because one never knows. So P equal to NP is, in our language of thing, mathematics complete. Okay. So moving along to more recent history, and now times when I was a grad student. How am I doing on time, actually? Let's see, maybe I'll put this in front of me. Okay, so I think I should be okay, still be able to field questions. So the modern complexity, we moved away from time as the most primary resource for measuring, restricting computation, to also thinking about randomness as a resource, both something that you can use to do things productively, but also to restrict as a resource to be used as an expensive resource, something that you should use frugally. So randomness has been noticed as being an essential resource in many related communities, in particular in economics and game theory. Not just fundamental results saying that every 2-player game has an equilibrium involves mixed strategies, and mixed strategies are randomized strategies. Players play using after tossing random coins. It's essential in distributed computing to enable coordination amongst multiple players. There are very easy results which say that most basic of distributional computing tasks cannot be solved in almost any reasonable modern communication network with some asynchronicity and some ability to fail. You cannot really get any coordination in a distributed system unless you use randomness, and randomness allows it to happen. And in cryptography, there is no notion of having secrets if you don't use some randomness. Your mother will know the passwords that you're going to use if they came out deterministically from you. So it's not going to work very well. So you should be using randomness in many places, and we do. And but the theory was, okay, this is great for computing, but it has nothing to do with proofs and nothing to do with logic. And this was the belief, or logic should not be something that's susceptible to randomness. This was the sense that changed only in the 80s. And the fundamental works that led to this was the notion of interactive proofs, and later also, and actually concurrently or even earlier, also the notion of zero knowledge proofs, which I'll mention in a moment. Due to works of Goldwasser and Mikari and Rakoff, who introduced this concept of interactive proofs in full generality, and Babai and Moran, who were also talking about interactions which were very limited number of rounds of interactions. And here the notion is, I'm not just a person out there to verify a proof that you've written down and gone away, but you have written down a proof and you're willing to stand by it and explain things about it to me, and I'm willing to ask you questions about it. How do you model this interaction, and does it give us any additional power? Early days, what we saw was actually there are a few problems for which interaction is able to find us proofs of statements that we don't know how to prove otherwise. Okay, so the simplest example of this would be graph non-isomorphism, or in a lay community, or if I wanted to prove to Shrikant that the notion of color does exist, I could take a red and a green colored object which look otherwise identical, and I'll give them to Shrikant, and he can hide them behind his back and pull out one of them. And if I can tell if it's red or green consistently, he knows which one is pulled out because he knows whether he's swapping them behind his back or not. I shouldn't know if these objects are identical, but if the notion of color exists, I should be able to tell it. This would be an interactive proof, which is sort of akin to the proof of graph non-isomorphism. And it's something that we just don't know of a classical way of proving it. I don't know how to write down this proof. Whatever is happening between Shrikant and me will completely convince Shrikant at the end if I was correct. And at the same time, there's nothing that we can write down over here that actually translates into a proof. So we explored this thing formally using the same mechanisms that we have been trained to use by Turing, by Karp, by Levin, by Cook, and raised this question of what is now an interactive proof verification. We were able to formalize this, and this led to this thing that if the verifier is not doing something random, then there's nothing really interesting. If Shrikant was not flipping those red and green objects behind his back randomly, if he was deterministically going to go left, right, I would be able to guess this. But because he's doing something randomly, this space has some additional power. And because the number of possibilities in terms of complexity, the number of possible questions that he can raise is exponentially many different questions, but in a polynomial amount of time, this rules out the option of writing down an answer to every possible question. So this Pepsi versus Coke thing that I just mentioned, there's also very interesting things. I mean, eventually we realized that this is a system that has amazing power. So I can prove to you that a theorem does not have a proof of length L in a length poly in L interaction, L squared length interaction. I can prove to you there is no proof of length L. Okay, think about this. This is our canonical co-NP problem, as we call it. This is if every theorem has a classical proof of length L, or length L squared, which says, look, there is no proof of length L, that would imply NP equals co-NP, something that we don't believe, but we can prove this statement interactively, and we can prove a lot more. And in fact, things that we can you can prove that a game of Go between two players is going to lead to an ultimate win for the black player based on interactively asking questions about the game. So for me, this is a very satisfactory result because there's a version, whoops, what did I do? Yeah. So there's a version of this result that tells us that playing mahjong or solitaire on your computer is as intellectually stimulating as playing chess or Go. Well, almost. Chess maybe depends on the sets of rules that we're using, but certainly Go for all known rules. And that's great for me because I really don't enjoy playing chess or Go with other people, and the fear of losing is too strong. But I'm just playing against computers, and that's completely okay, and I'm equivalently stimulating myself, okay? So this is a very interesting theorem in the space. So IP equal to P space, amazing statement that was proved, a very unexpected statement that was proved in 1990 by Lund, Fortran, Karloff, Nissan, and Shamir. By the way, I mean, as I mentioned earlier, the motivation for defining and creating this notion of interactive proofs, at least for Goldwasser, Micali, and Rakoff, was to define proofs that convey no knowledge other than the fact that the statement is true. Of course, if you know that the statement is true, there are logical consequences of this that you also know. We cannot take it away from that. So how do you define what you did not learn anything else other than what logically follows? It's not trivial to capture this concept. There was an entire capturing knowledge in addition to just what is an interactively sound proof, was both done in this beautiful work. Of course, Goldwasser and Micali got the Turing Award after this, and in part due to this work. They are also the first people to have told us that probability was necessary in randomness, probabilistic encryptions, in cryptography, and so many interesting lessons came out from their works. Bringing us back to this notion of a written proof, and we said, look, probability should not be helping with that, right? But apparently there is still one question where it does help. So that the proofs have to be read in its entirety in order to be able to verify it. And if you look at, on the web for various proofs, you can prove all kinds of interesting things, 2 = 1, pi = 3, etc. These are very, this is the canonical way of thinking about proofs. In IIT Delhi, we used to have this thing called a Rajpal transform, which is the line over here which does not follow from its preceding line, and you're always supposed to hide that transition on the transition of a page. So you go from page 1, which has everything, to page 2, which has the next line, and it will not be discovered. So these Rajpal transforms do exist in proofs as we know it. So how can you not have a reader, how can you have a verifier not read the whole proof and still be convinced that the final statement is actually true? PCPs actually allow us to do this, but in order to do that, we have to change formats. And recall, we come back to this notion of formats for writing proofs, okay? Proofs don't have a unique format in which you can write them. You get to choose the format, and in fact, we do actually know one global format already, which is we have to write proofs in English. Why in English? Is it, a proof written in Hindi or Tamil is not acceptable as a proof? Well, it's completely logically fine. It's just that the verifier may not know that particular language. Well, the verifier may not know many other things too, and so for each requirement of the verifier, as long as they are saying, look, there is a way of stating everything that is true in this format that I have specified, and as long as anything that's not true cannot be proven correct in this methodology, this is a reasonable format. So we can change the format, and we should be able to do that by changing this verifier. Okay. So the completeness and soundness of the verifier should be this. Whoops, what did I do here? Okay, let's see if I can do this right. So all we should ask for, if the theorem is true, then there should be a way to prove it. That's not good enough, right? Because remember the original example where we said, look, here's a proof and here's another proof, and the second proof just said L. Okay, so we want the proof to be mechanically verifiable, but we also don't want a proof which is like exponentially long in the length of the original proof. When you're translating between proofs, polynomial size translations are okay. Exponential size translations are not okay. They will completely ruin this gap between polynomial and exponential time, which is the only gap between theorems and their proofs. Okay, so we really want to preserve this difference that, oh, a proof is helping me verify, and in some cases the proof may not be necessarily to be too long, but in cases where it is very helpful, we shouldn't dilute its effectiveness by making the new proof exponentially long. So the proof has to be polynomially long, and if the statement does not have any proofs, then there should be no way of convincing the verifier. Now here we can also say, oh look, you don't want to convince the verifier with too high a probability. What probability over what? Not over the statement, that would be a disaster. Not over the proof, that would be still a disaster. It's over the random coins that are tossed by the verifier. This is within our control as verifiers. We get to choose our random number generator. If it's a bad one, then you should suffer its consequences. If it's a good one, then you will have the soundness guarantees associated with this. And if you don't like the probability of catching an error with being only half, run the same process a few times. That'll boost your probability because you get to resample your randomness. So if you do this, then you can actually find very neat theorems and proofs, and this is something that I was involved with during my graduate studies in works done with Arora, Lun, Motwani, Safra, and Segedi. We were able to show that there is a format for writing proofs which is which satisfies both of these conditions. There's only a polynomial blow up over the standard size. It has completeness, meaning valid statements have with valid proofs, and invalid statements which should have no proofs, will not be accepted by the verifier with probability greater than half. And the verifier only reads a constant number of bits of the proof. Okay? So this is work that was done in 92. And by the way, this thing we said was, okay, how many bits did we read in the proof? Maybe you could read just 3 bits, but in that case, maybe the probability of detecting an error might not be 1/2, it may be 0.00001. There was a number of zeros before the 1 is not something I'm committing to today. That's a lower bound on the number of zeros there, okay? So how did this proof happen? I will not be able to tell you any technical details, but let me at least give you a one-line explanation or one-slide explanation of how I think of it. It's like we're going to change the language of expression. Boole said, change all of logic, all of mathematics, and express it in zeros and ones. We're going to do it with elements of a finite fields and evaluations of polynomials. And what this ability to work with polynomials does is analogous to the following process. I could be inspecting this building for safety and security and saying, oh, look, is this construction stable? And one way to do it, I go look at every one of the atoms in the building and try to see what its interaction is with the next one of this atoms in the space, okay? Too many atoms in this building, I don't think this is going to be a feasible task for any inspector. That's not how they do it. What they do is they look at the building as a collection of walls, let's say, okay? I mean, any collection of rigid objects we'll consider a wall, okay? And there's constant number of walls in any one of these buildings, and inspect each one of these, and that's sufficient. And that's the similar thing that happens with this new format for writing proofs that we have over here. So the original view, building is a collection of atoms, is equivalent to saying a proof is a collection of bits. The new view, building is a collection of walls, is like saying proof is a collection of polynomials, but a constant number of polynomials. Okay? Every proof is a constant number of polynomials. And in order to verify that this whole structure is stable, I just need to say that these few polynomials relate to each other properly. I mean, this wall meets that wall at the right intersection and has the right rigidity at these points. And then you should also make sure that these walls are not made of sheetrock or something like that. So, you inspect these buildings at some random places. The complete analogous process is what builds us PCPs today, okay? So polynomials are what lead us to these walls. And instead of working with standard NP completeness, which should have said, oh, look, let's work with a graph and try to prove that it's three colorable. The PCP idea tells us that somehow you can express everything in terms of give me these four polynomials A, B, C, and D such that this operator, which when applied to these four polynomials is all zero. Okay? And that's the essence of PCPs. And now you can just verify this statement saying, oh, have you really given me polynomials? I have to check this. Are these really walls made of concrete rather than of sand? And are they satisfying the right integrality by just saying, are they kind of meeting in the right angles at various places? Okay. These two steps can be this analogy completely works out, and this proves the PCP theorem for us. The hardest part, of course, is building this stability test testing this ABCD or polynomials, which is a purely syntactic thing. It has nothing to do with the building that is being built or its functionality. Its design is I think the hardest part of it. The rest of it is good material for exercises. And by the way, this is the whole proof that I've flashed, which says why is graph coloring being NP completeness translate to the stability of four polynomials. That's the entire proof, but I will not read it for you. Okay, so yes. So work since then, PCPs have become better and better and better over the days. And the remarkable statement right now is the following. So the blow up in the size of the proof is barely superlinear. Okay, and barely superlinear I used to define as n to the 1 plus epsilon for every epsilon less than greater than 0. In fact, even more hot off the press is this result, which will appear maybe next year, hopefully. It's on archive already by Bafna, Vyas, and Minzer, which shows that the blow-up can be made even polylogarithmic. The verifier will be reading 3 bits of the proof, bits, 0 or 1, Boolean bits, 3 of them. And if the proof is correct, they'll accept with probability 1. If the proof is incorrect, they'll be accepting with probability nearly a half. Not quite a half, it's half plus any epsilon that you want. And amazing tools have gone into the space, things that we did not expect at all at the time. Fourier analysis was the first of these things, expanding graphs, error correcting codes, information theory, and most recently high dimensional expansion, HDX. All of these have become integral players, and they've, in fact, one could argue that many of these tools have been developed because of this connection to the PCPs. Okay. All right, so that's about as much as I wanted to say. Okay, maybe I do want to mention why do we care about PCPs? Well, in addition to being something remarkably surprising about logic as it can be carried out or should be carried out, they also give us a completely new look on optimization problems and have completely changed the perspective over there. So this new connection arose from some previous work of Feiger and others, and now our work with Aurora and others also led to further strengthenings of this connection. Solving optimization problems approximately, which is something that many of us would be happy with. You saw this tour visiting 13,000 cities. Did any of you check to see if it was optimal? It looked good enough, right? You probably, if you have to visit all those 13,000 cities for some reason, you would just go ahead and follow it because it doesn't look terrible. Approximate optimization is something that we are very, very happy with in many cases, but we are not able to do even that very nicely. And that was explained away. Why are we not able to do it nicely? Because finding an approximately good solution can be as good as finding an approximately good proof for a PCP, where approximation is measuring the probability with which the verifier will accept. And we know that approximating the probability with which a verifier will accept will distinguish true statements from false statements. So we cannot approximate it. So existence of nearly valid proofs implies the existence of perfectly valid proofs in the setting. And so many hard optimization problems are hard to solve. Okay, this has completely revolutionized our understanding of inapproximability at this stage, by the way. All right, modern directions. Let me just tell you a little bit about modern directions and also maybe tell you a little bit about what I think may be concerns in the future. So two things that I want to mention in ongoing directions, things where we still have a question mark. There's the unique games conjecture due to Cote. And Subhash Cote, whoops, again doing this, okay. Subhash Cote's conjecture, you can state it roughly as the following. You're given a bunch of linear equations, modulo some prime p, and you want to distinguish between the case where almost everything is satisfiable from the case where, basically the random assignment is the best. So a random assignment will satisfy 1 over p fraction of the equations, and you want to just say, look, can you beat that by a noticeable amount? We just want to distinguish between these two. Hofstad's theorem, the one that I flashed in a slide as part of this modern views on PCPs, already tells us that this is actually an NP-hard problem, even in the special case where every linear equation only involves 3 variables. What's the unique games problem? It's Subhash's conjecture, which says, well, what happens if you're only allowed 2 variables per equation? Well, we still think this is as hard, but we don't know how to prove this. And this is where the current frontiers of PCP theory seems to be charging up to. If we knew this, we would have a really, really broad class of optimization problems for which we know the best algorithm today. Okay, so we already have the algorithm working for us. We know how well it works, or in most cases we know how well it works, but we can run it anyway because this is going to be the best one. And that will be the best, provably best, if this conjecture was true. We don't know whether this conjecture is true or not. Why is it called unique in game? Well, it's inspired by a 2-prover proof system, a game, you could call it, where there's a verifier who talks to 2 different provers who are not interacting with each other. And this verifier is trying to verify if this system of linear equations is satisfiable or not. So what does the verifier do? He just picks a random equation, picks the 2 variables in those equations, and asks P1 for one of the variables and P2 for the other variable, and says, oh, look, tell me the values of these 2 variables. Then the verifier goes ahead and verifies if this linear equation was satisfied or not. Okay, because this particular equation, they have the ability to verify. This success probability of this verifier, of convincing the verifier, making the verifier accept, is directly proportional to the fraction of equations that's satisfiable by an optimal assignment. And but now this looks like a 2-prover game. And what makes it unique? It's unique in the sense that for every answer given by prover 1, there is a unique answer given by prover 2 that will be convincing the verifier. For every answer of prover 2, there is a unique answer of prover 1 that will be convincing the verifier. So this makes this a unique game. And what we don't know is if unique games can be hard to solve to within success probability nearly 1, where the verifier is going to accept with probability nearly 1 versus the verifier is going to accept with probability nearly 0, which is what will happen when p goes to infinity. So can you distinguish between those two? We don't know. That's the question that we are up against. All right. So, briefly, let me just say that Cote, Minzer, and Safra made dramatic progress on this, which is roughly analogous to saying instead of linear equations, you have quadratic equations involving 2 variables. And for that, they really proved this 1 minus epsilon versus 1 over p plus epsilon. But for linear equations, we don't know the answer, and that's where the open challenge lies. Another modern direction of work which is intimately related to interactions and proofs is this notion of quantumness. Can we build a quantum computer? And when we prove that we've actually built a quantum computer, okay, this has been like ongoing battle between the practitioners in the field of quantum computing for the last 20 years. But this was a question that was raised by Einstein, Podolsky, and Rosen. Einstein was a notable skeptic of the axioms of quantum mechanics and said, look, here is this remarkable thing that could be true, or this EPR paradox says, here's this remarkable thing that could experiment, which if we could implement would be, which would involve instant communication between players which are light years away, and they would be able to communicate faster than the speed of light. And this should not be possible, and so something is wrong with quantum mechanics. Over the years, we actually built experiments which convince us that we can do this. So this part of quantum mechanics is intact and it's definitely reliable. We are able to work with this. That's not a problem. But what's more interesting to our story today is that this was actually designing a two-prover interactive proof system along the same lines as the unique games problem, not necessarily satisfying uniqueness, but otherwise it is a two-prover. It's a game. And this game, I was articulated the variant due to C.H. Asich, and I forget who the authors are over here, but their version is the following. It's saying that, look, it's like a verifier talking to two players, Alice and Bob, prover 1, prover 2. And let's consider the setting where the verifier sends each one of them a bit. X is a bit, 0 or 1, Y is a bit, 0 or 1. Verifier just picks two random independent bits and sends them. The provers are supposed to send back two bits, A and B, and they can coordinate however they want before the game is set up to determine what their strategy is going to be for interaction. But once they've received the questions, there's no further interaction amongst them. The way you could set this up physically is to send Alice and Bob off to some very far away spaces, along with sensors which are measuring what they're going to say, and send them both questions. Takes time for the questions to reach them, that's okay. Instantly they're supposed to respond, and the sensors are sitting right there to record the instant responses. They do. And then you take your time to bring back the answers from the sensors and say, what did they say? So you look at their answers, they're supposed to be two bits, A and B, and the condition that you want is that X and Y should be equal to A XOR B. Okay. So no matter what kind of a classical strategy we can think of, there's nothing better than A and B always being 0. And that sort of takes care of the case where X and at least one of X or Y is 0. It misses out of the case where X and Y are 1, in which case, okay, you still got a 3/4 probability of success. Can we prove that this is the best strategy? The axioms of quantum physics, and this is what EPR actually were pointing out, that look, you're going to be getting some remarkable communication phenomenon, and it's true, you actually do get this remarkable communication phenomenon. Quantum strategies can succeed with probability something like 0.85 somehow. I don't understand how it works, but that's the truth. Modern extensions, we've been able to use interactions to prove that a certain system is actually quantum. So Mahadev's work in this area is very elegant and uses some amount of cryptography, but modulo cryptographic assumptions is really sort of a proof that there's quantumness, is a way in which you can prove that we are able to do some amount of quantum computing, build interactions, entanglement, and use them. There's this amazing work of G, Natarajan, Vedic, Wright, and Yuan, which shows that actually you can interactively verify all computable functions with a polynomial amount of communication, but the amount of communication is just sort of more or less, it's dismissible. It's like morally this is a constant amount of communication, and every computable function, so not even, so it doesn't have to be decidable or whatever. So, and a key ingredient in the result is something that's extremely, extremely interesting to physicists, which is that Alice and Bob, this same two particles that are trying to claim, players who are trying to claim that they have some entanglement amongst them, quantum entanglement, can prove to you that they have n bits of quantum entanglement, n qubits, without actually sacrificing the n bits in the process of proving it to you. We knew how to prove it, but in the process of proving it, we would have lost all that entanglement. So what's the point in proving that I have entanglement when I'm going to lose it? The new strategy now is somehow it's an amazing protocol which allows them to actually convince the verifier using very tiny amount of loss in this entanglement that there is entanglement. We have n entangled qubits, but we prove it using log n communication. So you can just see that our language of expressing things via interaction and proofs is able to capture many interesting phenomena in physics that the physicists did not even suspect, and now we can actually start thinking about implementing some of these effects. Okay. Very briefly, oh boy, I'm out of time, I'll take a couple of minutes. So a little bit of context. PCPs, which I really do love and like, we've been using it mostly as a method to prove things are not doable, a negative result. They should have really been positive, who likes to spend time verifying long, boring proofs? Why not use the fact that the verification can be much easier? And we do use it in some very specific settings like blockchains and so on, but we are not using it in day-to-day use. Why is it the case? And I think it's a sort of a change in a standard assumption. We usually think about saying, oh, look, our system of axioms is something tiny, we have a tiny proof, and then we have some huge theorem that we want to verify. The truth is, the world that we live in is the mathematics has a massive context. And in this context, like for example, there's this very nice quote from this book by Layton and Meyer, which says that, look, by some estimates, a proof that 2 + 2 = 4 in ZFC would be like 20,000 steps or something. So if this book were to start off proving that, the book would conclude proving that, and that would be the end of the book. So we say, okay, look, we have to assume a large common context. So this is the common phenomenon in all of the proofs, and I think it's something that's really like something that we as a community are capable of exploring. We haven't done much of it, and I do hope we will be able to look at this in the future. So I'll probably stop right there. Slide 12, okay. Boy, I don't know if I can go to there, but feel free to ask if you are, do you know heard of this? Okay. Is this the one?
Yes.
Theorem proving, the complexity of theorem proving as in, in the most natural sense. I give you a theorem T and a proof length L, and I say, is there a theorem of this? Is there a proof of T of length at most L? That problem being NP complete was shown by Cook, and he defined NP incompleteness to say that this problem is hard. Okay. Yeah.
Yes. I think like this way of, without trying to talk about explicit problems that are undecidable, you can just say that proofs are languages are sort of these things that correspond to uncountably many objects, and programs are they are like finite objects, so only countably many. So there has to be things that are uncomputable. Is there a similar way to also reason about unprovable statements?
So good. So the question was really, can you not prove some of the Gödel theorems by just talking about the space of things that are actually countable or not? I think, okay, so just like a proof based on counting would not prove to you that pi is not algebraic. It's a very similar kind of a concept that shows up, I think, in the provability setting. Also, there is a space of things that are true, which I don't know that the set of true statements. I don't know how you would prove that the set of true statements is uncountable. So yeah, I don't know how to use just sheer counting to prove that the space of provable things is clearly countable, but I don't know space of true things is countable.
When can we start using PCPs to review conference papers?
When can we start? After you solve this last problem of mine, which I didn't get a chance to expand upon, but I really think that there is a massive amount of context that we work with, and also we use the context in non-trivial ways in order to verify proofs. I mean, we've sent papers to journals and come back with two reports, one of which says the paper is beautifully written, the other one says the paper is incomprehensible, and it's the same paper, right? So how can this happen? It's because of the different contexts of people and the different derivations that they're willing to use in order to verify a proof. These are all like remarkably the ability of what a human mind can or cannot verify, or even an AI can or cannot verify, seems to be like very fickle. So I think it's going to require a fair amount of exploration and investigations. But I think there are very interesting questions here. It's not out of scope for us to explore them.
Okay, so those of you who haven't had a chance to pick up a kit, you can also register, and copies a little further down. We like to make sure you walk around a bit, so follow the volunteers. It's a little further away, it's not right outside.